We're going to use problem 3 from Cengage Now Homework 15 to demonstrate multiple regression. The data is simulated. We have quantity demanded of lobster, which is basically how much is purchased by consumers. We have the price of the lobster that the restaurant charges. And then we have average customer income. So we're going to copy the data and paste it into Excel. Our Y variable is quantity demanded. How much people consume depends on the price, which is variable x1, and customer income. So we have multiple regression because we have two x variables. And we use these two x variables, which is our model, to predict the quantity that our customers are going to consume. Now, going back to Cengage Now, the first question is to compute the means of the above variables to do decimal places. So I'm going to calculate the means. So maybe I'll insert a column here. I'll put means, and I'll put standard deviations. Min and max. Usually when you summarize data, you calculate the averages, the standard deviations, and then the maximums at the minimum. To calculate the mean quantity demanded, you type equal average. So calculate the standard deviation. You type stdv.s for sample, s for sample, and then highlight where the observations lie. For the min, you just type equal minimum or min. For max, equal max. And then I also want the correlations. I want the correlation of quantity demanded versus the correlation of lobster price. Notice the correlation between quantity demanded and lobster price is very high. It's really close to -1. Next, I'm going to calculate the correlation of quantity demanded and customer income. The correlation for that is between how much is produced or purchased and customer income is positive, but the correlation is not as close to 1 as it is for price. So the correlation suggests that maybe the price is more important than our customers' income. Now, I also want to calculate the correlation between the x's. The correlation is between the two x variables. The correlation between the two x variables is -0.443. Now that correlation is large, say -0.9 to -1 or 0.9 to 1, then there might be a multicollinearity issue. When the correlation of x variables gets above 0.7, multicollinearity becomes a problem. But I think most microeconomists who do millions and millions of observations would probably prefer that we include highly correlated independent variables, then exclude them, because then your regression will suffer from what is known as omitted variable bias. Okay, now that I got the means, the standard deviations, the min, the maximums computed for quantity demanded, I can very easily compute the same for lobster price and customer income. So the first mean I need is the mean quantity of lobster. To 2 decimal places. Copy the mean lobster price. And then copy the mean customer income. Okay, so that should be all correct. Now I need to use Excel to perform multiple regression analysis. And I need 5 decimal places for all but the degrees of freedom calculations. So I'm going to go do multiple regression. So I'm going to maybe put a box around this to indicate that this is a table. And then this up here, I'll make that yellow because that is our y variable. And I'll make this, I don't know, peach, because our model is now 2 x variables, or 2 independent variables. So to do multiple regression is just like doing simple regression. You hit the Data tab, then you click on Data Analysis, and you scroll through until you see Regression, and you hit OK. Now my y variable, I'm going to load my y variable by highlighting quantity demanded and the 8 observations below the phrase quantity demanded. I'm going to load my x range by clicking on the label for lobster price and customer income, and then scrolling down to the 16 observations that are below these 2 labels, or the 8 observations that are below those 2 variables. Make sure labels is clicked. Click on residuals. We will have to compute residuals for this particular problem in this Engage Now. And then for the output range, click on that white area, click the button, and I'm going to put it right below my summary statistics table. And then you can hit OK. Now, in Cengage Now I said to 5 decimal places, right? 5 decimal places for all but the degrees of freedom calculations. So I'm going to highlight everything but integers. And then I'm going to shrink the number of decimal places to 5. Okay. Now the first thing I want to fill out, the first table I need to fill out is the Anova Table, what is called the Anova Table, or Analysis of Variance Table. I have sum of squares, degrees of freedom, and mean square columns. So this value here is the sum of squares due to regression. So sum of squares due to regression, in my case 399.36426, is that value. The sum of squares due to error, now Excel refers to it as sum of squares due to residual. A residual is just an estimated error. So most regression packages call this error, sum of squares, or sum of squares error, SSE. So I'm going to change that to error. So you don't, this is SSR, this is SSE, and this is SST. Leaving that as residual may confuse people. Because again, this is SSR, this is SSE, and this is SST. So the SSE, sum of squares error, or error sum of squares, is pasted right here. And again, a residual is just an estimated error. I need the SST. The SST, if divided by n minus 1, in this case n is 8, the SST right here, divided by n minus 1, which would be 7 in this case, that is called the variance, sample variance of the y variable. Now we need to get the degrees of freedom. Excel likes to put them in the column before the sum of squares. It likes to put them in the first column. I prefer to put them after the SS, sum of squares column. So the first one's 2, the next one's 5, and the last one's 7. So 2, 5, and 7. Why is this 2? Well, how many x variables do we have? We have 2 x variables. So that's why that is 2. Why is this 7? Well, we have 8 observations. Here's observation 1, observation 2, yada yada yada, observation 8. 8 minus 1 is 7. Again, if I take the SST and divide by 7, I get the sample variance of the y variable. I'll get the sample variance of this. Now, why is the error degrees of freedom 5? Well, again, we have 5 observations. 1, 2, 3, 4, 5, 6, 7, 8. And we've estimated 3 parameters. We're going to estimate the intercept, the coefficient that goes with lobster price, and a coefficient that goes with customer income. So 8 minus 3 is 5. Notice that 5 plus 2 is 7. Also notice that 23.5 plus this number is the SST. So the SSE plus the SSR equals the SST. 2, the degrees of freedom for the regression, the error degrees of freedom, if I add those together, I get 7. Now the mean square due to regression is just this number, SSR, divided by this number. So you simply just take this, divide by 2, and you get the mean square error. Excel already has it though, 199.68. The mean square due to error is 23.51 yada 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 divided by its degrees of freedom, which is that number. And Excel already has that number as well. The F-Stat is a ratio of variances. This is an estimate of a variance, and this is an estimate of a variance. You can think of this as the variance of the y-hats. You can think of this as the variance of the predicted quantities demanded. So these right here are the predicted y's, and notice that they're really close to the quantity, the actual quantity demanded. So you can think of this right here, you can think of that intuitively. This number here is the variance of this variable, which we call y-hat, or predicted quantity demanded. And you can think of this as the variance of the errors, or residuals. So the variance of this column intuitively is this. The variance of this column is that. And if I divide the SST by 7, I get the variance of y. So again, the variance of y is SST divided by 7. The variance of the residuals is the MSE, which is the SSE divided by its degrees of freedom. And then the MSR is the variance of this column, which is found by dividing the SSR by its degrees of freedom. Now, like I said, the F-stat is a ratio of two variances. So the F-stat is just this number, the MSR, divided by the MSE. And I can show you that that works, right? The MSR divided by the MSE. And you get the same number, see? Now, in multiple regression, this F-statistic is not equal to the square of a t-stat like it is in simple regression. Why? Because we have two t-stats. However, you can kind of think of it as if I square both these numbers and I kind of like average it, you know, think about it as an average, or maybe the sum of these two squared. Generally speaking, the bigger the square of these values, the bigger this is going to be. Now this is going to be pretty small when we square it, but this is close. This is over 64 when we square it. So maybe you can think of it as the average t-stat square, right? Generally speaking, if these are large after you square them, the F-stat's going to be large. Okay, so I need to copy the F-stat into my Anova table in Cengage Now. My Anova table is now done. I can go fill in the coefficient table. In the coefficient table, I have B0, B1, and B2. B0 is the intercept or constant. B1 is the slope coefficient for the variable lobster price. And B2 is the slope coefficient for customer income. This value is the estimate of beta 0. This value is going to be the estimate of beta 1. And this is going to be the estimate of beta 2. We're going to go ahead and get those. So the intercept is 107.7 yada yada yada. So B0 is 107 point yada yada yada. That is an estimate of the true beta 0, which we cannot know. Only Greek gods know the values of the Greek letters. B1 is negative 0.85619. That is the estimate for beta 1, which would be the true value of the slope coefficient for lobster price, which we cannot know. But we can estimate it, and this is the estimate of that beta 1. The estimate of the beta 2 is negative 0.00106. That is B2. It estimates beta 2. Next, we want to get the standard errors. The standard error of the intercept is 5.38251. The standard error of lobster prices estimated coefficient is 0.10048. And the standard error of customer income's estimated coefficient is 0.00170. So you can think of these, and these coefficients, these estimated coefficients, are analogous to the x bars, the sample means we computed in Chapter 9 to estimate mu, the true population means. And these are the standard errors. So if I divide this coefficient by the standard error, I'm calculating the test statistic for a hypothesis that wants to know if these betas are equal to 0. So 107 0.7 minus 0 divided by the standard error is the test statistic. This minus 0 divided by the standard error is a test statistic. This minus 0 divided by the standard error is a third t test statistic. And each one of those tests would be testing the hypothesis that the corresponding beta is equal to 0. Now I can show you, I'm going to delete this part here. Again, if I take the estimated coefficient minus 0, in this case just the estimated coefficient, and divide that by the standard error, I do in fact get the t-stat. And that's the case for all of them, right? This equals that t-stat, this ratio equals that t-stat, and this ratio equals that t-stat. So the first t-stat is more than 20. The next t-stat is negative 8.5, something, something, something. And then the third t-stat is negative 6.2678. And I'm just copying and pasting. Now here's something that's kind of interesting. Ignore for the moment the negative signs. We got a t-stat close to 0, we got a t-stat close to 9, and we got a t-stat close to 20. What happens to p-values? As the t-stat rises in value, the p-values get smaller. When the p-value is really, really tiny, the t-stat is way out in the tail of the t-distribution. Here, the p-value is really, really tiny. The t-stat is way, way out in the tail. Here, the p-value is 0.5. The t-stat is in the hump. And when the t-stat is in the hump of the t-distribution, this coefficient is essentially considered 0. When the t-stats are very, very, very large, these are not considered 0 in a statistical sense. Okay, what's the next thing we've got to do? We have to get the residuals. What are the residuals? Well, I had the residuals computed, right? So this is residual 1, residual 2, residual 3, residual 4, residual 5, residual 6, residual 7, and residual 8. What I'm going to do is I'm going to copy this stuff. I'm going to put it up here next to the data. Okay. And then I'm going to just double click on this number here. Or actually what I'm going to do is I'm going to do this. I'm going to take the observed quantity demanded and I'm going to subtract off the predicted quantity demanded. And the difference is the residual. You guys see that? And you can think of the residual as the estimated error. The model's not perfect. We are omitting important information. Maybe we're omitting where the restaurants are located. Maybe these are 8 restaurants. Maybe some of these restaurants are located in really affluent neighborhoods. Or maybe they're located in certain parts of the country. Maybe this restaurant is located in Maine, where there's lots of lobster. Maybe this restaurant's located in Utah, where there's not a lot of lobster. So we're omitting important information, which is why our residuals are not all 0. This is a measure of the error in the model for a particular observation. And we can finish calculating all these residuals that Excel has already calculated for us, right? So Excel essentially plugs this into our equation here to get the predicted value, and then Excel takes the observed quantity demanded and subtracts off the predicted quantity demanded to get the residual. So I'm going to go and delete that and then go down here and get the residuals. I'm going to copy them one at a time into Cengage now. And we only need 2 decimal places, so let's fix that first. So we only need 2 decimal places. So negative 150, first residual, The second residual is negative 160. The third estimated error is 316. The fourth estimated error, 1.92. The fifth residual, negative 2.09. The sixth residual, negative 0.56. The seventh residual, 0.61. And the last one, 0.08, or 0.07, sorry. So the model appears to have done the best with observation 8. So this observation appears to be estimated quote-unquote best, where the worst observation is the third one. It has the biggest error. So this has the biggest error. And maybe that's in a affluent area in Maine or Massachusetts. So maybe we can include a dummy variable that would indicate whether the restaurant was located in New England along the ocean. And maybe that would reduce this error and that error. Now, I want you to sum the residuals. So what you're going to do here is right below this column, you're going to write equal sum. And notice that the residuals are 0. So we'll go back to Cengage now. And that's exactly what we expect, right? One of the error properties is that the residuals add up to 0, or the average of the residuals is 0. What does that mean? Well, anytime we have a large negative residual, we're going to have something that offsets it. Anytime we have a small residual, we're going to have something that offsets the positive one with a negative. So they kind of cancel each other out. Now, I want you to square each of the above residuals. So we're going to square these in Excel. So these are the squared. We'll call them squared errors. Squared errors. To square it, hit equal and then C44 because that particular residual is in cell C44. And then hit Shift 6, which gives us what we call caret. That caret says raise C44 to the second power. So the residual here is now squared. I'm going to reduce the number of, decimal places. And then to get the rest of the squared errors, I just grab that bottom corner and pull it down. The next question, it says square each of the above residuals. Sum the squared values. So we got to sum them, right? So the sum of the squared errors, we call that the SSE. I notice this number 2351 is that number right there. Okay, so I'm going to copy that number. I'll paste it in Cengage now. Now the next question says this value equals sum of squares due to regression, sum of squared errors, sum of squares total, mean square error, mean square due to regression. That's the SSR. It doesn't equal that, right? The SSR is that. Mean square due to regression? No. Mean square error? Nope. Sum of square total, SST? No. It equals the sum of squared errors. Which makes sense, right? Because how do we get it? We squared each of the residuals, or estimated errors, And then, what do we do after we squared them? We sum them. So sum of squared errors. Nothing magical about that phrase. Now, the standard error of the regression is from the regression output table. Excel has standard error in two different places. It has standard error here, and it has standard error down in our coefficient table. This is the standard error of the intercept, the standard error of the first coefficient, and the standard error of the second coefficient. This refers to the standard error of the regression. So we're going to paste that right there. And we only need 3 decimals, right? Oh, some of the squared values, some of the squared errors needs to be 3 decimals. So I need to go down here, change that to 3 decimals. So 23.511. And the standard error of the regression needs to be in 3 decimals. So the standard error, these will shrink down to 3 decimals. So standard error of the regression is 2.168. We're going to paste that right here. The coefficient of determination is the R square. The R square is 0.944. The adjusted coefficient of determination. Now, because the R square will rise toward 1 if you just add a bunch of unimportant variables, the R square has to be adjusted for this process. That's why they call it the adjusted coefficient of determination, or adjusted R square. If your goal is to make the coefficient of determination 1, you can just include a bunch of irrelevant information and you can get a high R square, which doesn't mean you built a good model. So you have to adjust for the number of variables that are added to the model. And the adjusted R square is 0.922. It's slightly lower than the R square. Okay. Now, in multiple regression, you interpret the adjusted coefficient of determination. In simple regression, you interpret the coefficient of determination. So we're going to use this number here to interpret how well the data is fitting the model. So we're going to multiply this by 100. And so now this number here implies that 92.2% of the variation in the y variable, and what is the y variable here? Our y variable is quantity demanded, is explained by our model. And what is our model? Our model is X1 and X2, lobster price and customer income. So lobster price, average customer income, and price of lobster. Okay, so the adjusted coefficient of determination equals 0.922, the adjusted R square, multiplied by that by 100. When you multiply by 100, you get 92.2%, and that 92.2% implies that 92% of the variation in the y variable, quantity of lobster sold in this case, is explained by the model, which in this case would be average customer income and price of lobster. In part D, we're going to perform 2 tests of coefficient significance. One for lobster price and one for customer income. The first one's for the price of lobster. The test for coefficient significance involves using the null hypothesis, beta 1 equals 0. The alternative hypothesis would be beta 1 not equal to 0, or beta 1 less than 0, or beta 1 greater than 0. Now, we cannot know beta 1, but we've estimated B1, we've estimated it with B1, which equals negative 0.85619. The alpha level we're going to use is 10%. And because this is a two-tailed test, we divide it by 2. So we're going to be in column 0.05 of the t-table. And since we have 8 observations, and we've estimated beta 0, beta 1, and beta 2, we're going to be in row 5. Row 5 is our degrees of freedom. These are also the degrees of freedom of the sum of squares error. Now, the negative 2.015 and the 2.015 come from the t-table. Remember, we're in column 0.05 because our alpha is 10%, two-tailed test divided by 2. We're in column 0.05, and then our degrees of freedom is equal to 5. So we have a critical value of 2.015, and because it's a two-tailed test, we make it positive and negative. And that defines our do not reject the null region. We have 0.05 here, 0.05 here. This is significance when I add 0.05 to 0.05. Now the t-stat, recall, is the estimated coefficient, B1, which estimates beta 1, and its standard error. In our table, B1 was that, and our standard error was 0.10048, and their ratio was the t-stat negative 0.852071, which is what I got here. Now, because negative 0.8521 is in the lower tail, the null hypothesis for beta 1 is rejected at 10% significance. In other words, because the test statistic is not in between the critical values, the variable price of lobster is not an insignificant predictor. In fact, it is a significant predictor. What that means is when the price of lobster goes down, we expect the quantity demanded of lobster consumed to go up. So, in part D, we're going to put in the test statistic to 2 decimal places, negative 0.852, because the null hypothesis of this test is rejected. We rejected it 10%. The quantity of lobster, or the price of lobster, has a significant negative effect on quantity of lobster sold. Negative, we say negative, a significant negative, because the test statistic is so far away from 0, I mean it's way out in the lower tail. We say negative because the test statistic is negative. So, in summary, because the null hypothesis of this test is rejected, the price of lobster has a significant negative effect on quantity of lobster sold. And that right there is evidence in support of the law of demand. Remember, for microeconomics, when the price goes up, the quantity goes down. If the price goes down, the quantity sold goes up. Next, we're going to do the test for beta 2. Again, we can't know beta 2. We can estimate beta 2, and we did estimate beta 2. We estimated beta 2 at negative 0.00106. Everything but the test statistic on this slide is identical to what it was on the previous slide. The critical values are the same for both tests. Why is that? Because significance doesn't change. It's a two-tailed test. We have 8 observations, and we estimated 3 parameters, beta 0, beta 1, and beta 2. The thing that does change is the test statistic. The estimated coefficient to 1 decimal, or 3 decimals, is negative 0.001. The standard error is 0.0017. or 0.002. The test statistic is the ratio of the estimated coefficient and the standard error, which we did here. We took the ratio of the estimated coefficient for beta 2 and divided by its standard error, which yielded the test statistic. Now, because the test statistic is inside the critical values, the coefficient beta 2 is insignificant. In other words, customer income with my data suggests that customer income is an insignificant predictor of quantity demanded. Now, that may not be the case for your regression, because remember, we all have different data. So here, the null is not rejected at the 10% level. So let's go back to Cengage now and answer those questions. The test statistic for average customer income equals, what was it? To 2 decimal places? Negative 0.63. Because the null hypothesis of this test is not rejected, we say average customer income has an insignificant negative effect on quantity of lobster sold. Why insignificant? The test statistic is under the hump of the t-distribution. It's inside the critical values, but it is negative, so the effect is insignificant and negative. In part E, we want to test for model significance. The hypothesized true model is y equal beta 0 plus beta 1 times x1 plus beta 2 times x2 plus an error term. We cannot know the betas. We estimate those betas with the b's, b0, b1, and b2. In this example on Cengage Now, our model is y, the quantity demanded, equal to a linear function of lobster price, x1, and customer income, x2. So our model includes 2 x variables. So when you're testing for overall model significance, the null hypothesis becomes beta 1 equal to beta 2 equal to 0. Now notice that beta 0 is not included in this test. Beta 0 is not included in this test because if this null hypothesis is true, then beta 1 and beta 2 are both 0, which would mean that beta 0 is actually the mean of y. It's beta 0 would be the mean of quantity demanded. If that is the case, then B0 would be pretty darn close to the sample mean of y. But that is not the case here, is it? The sample mean of y is 81.88. B0 is 107. So this tells me that I'm probably going to end up rejecting this hypothesis. Now the F-Stat, if you remember, is the ratio of what you can consider the variance of y hat and the variance of the estimated errors. And remember back in chapter 11 when we were testing the equality of variances. If these variances are equal, then the F-Stat is going to be close to 1, which puts the F-Stat in the hump of the F distribution. So the alternative hypothesis for this test would be that one of these betas is not 0. That's equivalent to saying that this variance is bigger than that variance. So the one way to state the alternative hypothesis for this model significance test is that the variance of y hat is larger than the variance of the residuals. That's equivalent to saying that the alternative hypothesis, beta 1 or beta 2, is bigger than 0. So the F test is an upper tail test because we're essentially testing whether this variance is bigger than that variance. The degrees of freedom in the numerator is 2 because the MSR has 2 degrees of freedom. The degrees of freedom of the denominator is 5 because the MSE has degrees of freedom equal to 5. This is the numerator of the Fstab. This is the denominator of the Fstab. So this is the denominator degrees of freedom, and this is the numerator degrees of freedom. According to Cengage now, the significance level is 10%. It is a one-tailed test. We don't divide the alpha by 1. So we have to go to column 2, row 5 and point 1 in the F table. So you have 2 degrees of freedom in the numerator. You have 5 degrees of freedom in the denominator. The alpha level is 0.1. So the critical value is 3.78. Notice this value is bigger than 1 because the F table is a table of upper critical values. So the F critical value for this test is 3.78. 3.78 separates the distribution into the do not reject the null region and the reject the null region. The upper tail area here, the significance level, is 0.10. The F-Statistic, remember the F-Statistic is 42.6614. Again, it's the ratio of 2 variances, and we're essentially asking the question, is the variance of y hat greater than the variance of the errors? With an F-stat of more than 42, we're clearly in the upper tail of the F distribution. So that 42.466 says the MSR, the variance, if you will, of y hat is much, much, much larger than the variance of the errors. So the model seems to be explaining a lot of the variation in y. And the variation in the residuals is very, very small, relatively speaking. So we are going to reject the null at 10% significance. And we're going to conclude that the model is insignificant, or another way to say that, the coefficients are not all equal to 0 simultaneously. So I'm going to copy the F-statistic value. I'm going to copy that. I'm going to paste it into... Oh, I need 2 decimal places. Sorry. I'm going to reduce that to 2 decimal places. I'm going to copy that into the critical value of the test for model significance. Oh, the F-statistic equals 42.47. The critical value, I'm going to have to get that from my PowerPoint. The critical value is 3.78, correct? I'll get that from the table. So the critical value of the test for model significance is 3.78. The test statistic is 42.47. Because the null hypothesis of the test of model significance is rejected, the model, comma, the model's what? The quantity of lobster regressed on average customer income and price of lobster? Yeah, that's the model, right? The model is the quantity of lobster regressed on average customer income and price of lobster. And that model is significant. Now, if Blue Lobster Bar and Grill charges a price of $27.64 per lobster, and the average income is $2,051.7 today, the restaurant will expect to sell blank lobsters. So on this, what we have to do is I'm going to copy these back into Excel, and I'm going to go down, I'm going to go right here. I'm going to paste them right here, and I'm going to insert some rows. We have to compute a predicted value where the price is 26.74 or 27.64. And average income of its customers is 2,051.7. Okay, so these are the values from that final problem, correct? 27.64 and 2,051.7. Okay, so if the price is that and the average income is that, what is the expected quantity of lobster sold? Now the way you do this is I'm going to hit equal, I'm going to go up to the intercept, and then I'm going to hit plus. Then I'm going to go arrow up to the price of lobster, and I'm going to hit times. I'm going to multiply that price of lobster, the thing in the green box, by the lobster price coefficient. And then I'm going to type plus, and I'm going to take the average income and multiply that by customer income's estimated slope. And when I hit enter, I'm going to get the expected quantity of lobster demanded, also known as Y hat. And I get 81.877. I need, we'll try 2 decimal places. I got to fix that. Check my work. Yeah, 2 decimal places works. We made a mistake up here. The test statistic is 42.47 to 2 decimal places, but we need 3 decimal places. So 42.466. So change that to 42.466. And then I think I forgot to put in the critical values of the test for coefficient significance. Critical values for the test of coefficient significance were 2.015. Right, from the T-table, correct? Sorry about that. So now, suppose instead Blue Oyster or Blue Lobster Bar and Grill had charged a price of $28.64 instead. The restaurant would have expected to sell how many lobsters? So all we got to do is notice that the difference between these two prices is $1. So I'm going to go back to Excel, and I'm going to change that to $28.64. And the expected quantity fell slightly, right, to 81.02. Copy in 81.02 that the law of demand holds. Notice the price was $27.64. The restaurant expects to sell 81.88 lobsters. But when the price rises to $28.64, the restaurant expects to sell fewer lobsters, 81.02. Now I'm going to check my work with the corrections made above. You can see that all the check marks are green. It gives you a really nice warm feeling inside when you get all those green check marks.